her PhD from University of Roorkee in 1988. She has been a national scholarship holder and postdoctoral from Loughborough University, UK, assisted by international bursary funded by Commission of European Communities. She has won numerous awards like Khosla Research Award, UGC Career Award, Star Performer of IIT Roorkee Faculty, Best Paper Awards by Railway Bulletin of Indian Railways, Special Facilitation in Memory of late Professor M.C. Puri, AAIP Excellence Award. She is one of the 4 women from IIT Roorkee to feature in the e-book Women in STEM 2021, celebrating the contributions made by 50 Indian women in STEM, published by Confederation of Indian Industries. According to Stanford University, she falls within top 2% of the scientists in the world for 2019 and 2020. She has authored 2 books, supervised 20 PhDs, and published 125 research papers. She is a senior member of ORSI, CSI, IMS, ISIM. She is the editor of International Journal of Swarm Intelligence in the Science. She is the associate editor of Swarm and Evolutionary Algorithms elsewhere and is on the editorial board of many reputed journals. She is the founder president of Soft Computing Research Society, India. She is the general chair of series of international conference on soft computing for problem solving. She has a vast teaching experience in mathematics, operation research, numerical and analytical optimization, and many more such related subjects. Her research interests are nature-inspired optimization techniques, particularly evolutionary algorithms and swarm intelligence techniques, and their application to solve real-life problems. Now I request Professor Kusum ma'am to kindly start with her lecture. Also, I request everyone present here to kindly mute your speakers during the lectures so that we can hear the lecture comfortably. Queries related to the lecture can either be asked in the chat box or at the end of the lecture. Now I request the host to make Professor Kusum as a host so that she can deliver her lecture. Professor Kusum ma'am, you can now start your lecture. I request Professor Kusum ma'am to kindly start with your lecture.
She is about to join in a moment. There was some internet issue, but she will be shortly joining us. Please.
Okay, sir. Okay, sir.
Wait for a while.
Okay, sir. Thank you.
Dear participant, please wait. Speaker is coming. Due to some technical problem, he is not able to join. Just 1 minute, we are going to start first session.
वेबएक्स वाला होगा। जो एक ही लिंक है वो व्हाट्सएप पे भी है, उस पे भी वही है।
Is it okay? Can you see me now?
Yes, madam.
Okay, great.
There was some technical issue with
Yeah.
Professor Kusum. He has joined now. Please unmute your mic. Madam, you can.
Hello, everyone. Good morning to everyone, and I'm so sorry for the technical hitch. It's the part and parcel of life. So I think I'm already late. So shall I begin the talk?
Yes, madam.
Okay, thank you so much. So let me just share my screen. Let me know if you can see my screen. So can you see my screen?
Yes, madam.
See it, ma.
Yes, ma'am.
Okay, great. Thank you so much for inviting me to this very important event. It is my proud privilege to address this international gathering. The topic of my talk is fundamental advancements and some open problems in the area of nature-inspired optimization techniques. So this topic is my research area for a couple of years, and it is closely related to the topic of this particular international conference. So what are the learning outcomes in this particular talk? I will be quickly introducing the concept of nature-inspired optimization techniques, and then I will share with you some success stories highlighting the application of nature-inspired optimization techniques in real life. And I'll give you a general template for nature-inspired optimization techniques with the help of a working example with the three randomly selected nature-inspired techniques, that is the particle swarm optimization, the gray wolf optimization, and the artificial bee colony optimization algorithm. And towards the end, I will discuss some open problems for researchers in this area who would like to build up a career in this area of nature-inspired optimization techniques. And then I'll close my talk with some research work at IIT Roorkee and some announcements. So let's begin. First of all, we need to understand what do we mean by optimization. In general, I would say that optimization is the art and science of choosing the best strategy amongst multiple options. For example, in this particular diagram, we can see that these people want to climb the hill, and there are multiple ways in which it can be done. So according to the user, which is the best strategy so that the hill can be reached is nothing but a simple layman's understanding of optimization. It has basically the number of applications in real life. For example, the optimal design of machines, minimization of cost, maximization of reliability, least squares, and optimization of neural nets. So the list is endless as far as the application is concerned. Particularly what we are talking about machine learning these days, a lot of work is being done in the area of artificial intelligence and machine learning. So there we have number of situations where we want to figure out some classification, some feature selection, some regression analysis, topology optimization, and of course, training the neural nets. So the question is, why such fuss about the nature-inspired techniques? Why are they preferred over the traditional optimization algorithms? The reasons are manifold. Firstly, the nature-inspired techniques can deal with non-differentiable functions, in fact, discontinuous functions as well. They can be applied to non-separable functions, mathematically speaking, also to rotational functions and ill-conditioned problems, and of course the NP-hard problems. Now coming to the characteristics of real world problems, we can see that since our objective is to solve real world problems with the help of the nature inspired techniques, we need to understand what are the characteristics of the real world optimization problems. First of all, most of the real world optimization problems are in general non-differentiable, and they must be having a couple of constraints, whether they could be linear or non-linear. There could be the situation when the search space is discontinuous or discrete. Also, there could be the presence of mixed variables. That is to say, some variables are continuous, some are discrete, and some are permutation. Of course, the problem of large dimension also comes into existence when we are talking about real world problems. And in my opinion, most of the realistic situations are encountered where the objective functions are multiple. Instead of one objective function, there are multiple objective functions which have to be minimized or maximized simultaneously, where the search space may be common. Of course, the theory talks about the various classifications of the optimization problems that exist in nature. And this is dependent upon the type of the decision variables, the number of the decision variables, the degree of the nonlinearity of the objective function, the presence of constraints, the presence of optima, and the presence of number of objective function criteria, etc. Based on these characteristics, the nature-inspired techniques have been classified into the following categories: unconstrained, constraint, multi-objective, multi-solution, and dynamic methods. Now, coming to the mathematics behind all this, let us first of all define what do we mean by the most general nonlinear optimization problem. In general, we can say that any n-dimensional function, that means f is a real valued function which is defined on n tuple, that is x1, x2, xn, is to be maximized or minimized subject to a set of constraints which is defined by S, and it may consist of, let's say, m number of inequality constraints and L number of equality constraints, as well as the lower and the upper bounds on the decision parameters. So this is the most general nonlinear optimization problem. In fact, the model, the mathematical model of the nonlinear optimization problem in general. Coming to the kind of solutions this might have. So this problem has two types of solutions. One are called the local optimum solutions, and the other are called the global optimum solutions. The difference between the two is that the local optimum solutions are supposed to satisfy this inequality. F of x is greater than or equal to f of x bar for each x belonging to D intersection n epsilon x bar. Means D is the feasible domain and n epsilon x bar is the epsilon neighborhood of this particular point x bar. So x bar is said to be a local optimum solution if this condition is satisfied, and it's called a global optimum solution if this condition is satisfied in the entire search space. So D is the search space. If it is satisfied in the entire search space, then it's called as a global solution. And if it is being satisfied only within a particular neighborhood, within an epsilon neighborhood of the point x bar, then it's said to be a local optimum solution. This is a pictorial representation to illustrate what do we mean by global solutions and local solutions. And in fact, there could be also some situations where the necessary condition is satisfied, but the sufficient condition is not satisfied, and these points are called the stationary points. Another example to illustrate the difference between the local solutions is illustrated with this two variable problem. We have the x1 versus x2 on this axis, and on the vertical axis we have the objective function, and we can see that there are a number of hills and valleys illustrating the local and the global optimum solutions. In literature, there are a number of benchmark problems which illustrate the complexities that might arise in these kind of mathematical functions. So, for example, the Eclat problem is a famous problem which has a number of minimas, and in fact, the number of local minimas is not known, although the global minima is located at the origin. This is a scalable problem, which means that n is the number of decision variables, and this problem can exist for n is equal to any positive integer. For n is equal to 2, this is what the objective function looks like, and as you can see, the hypersurface of this objective function has number of it has a flowery shape, and there are a number of local minimas as well, but the global minima is located at the origin. Another such problem is called the Grivank problem. This is also called in the category of the scalable problems. And similarly, the Rastringen problem is also of the same category, because there is a sinusoidal term which is responsible for these up and downs. Rosenbrock problem is a unimodal problem, but the complexity arises in the fact that it has a saddle point at this 1, 1, 1, 1. Again, it's an n variable problem, and depending upon the n, as in how the value of n increases, the complexity of the problem also increases. This diagram illustrates only for n is equal to 2. And finally, the Sheffel function is also one of the interesting problems because of this absolute value sign under the square root, which gives it this kind of a shape. So as I said, with this kind of complexities that are occurring, mathematically speaking, since our objective is to solve real life problems arising in various disciplines, we want to design optimization algorithms such that they can consist of the various features which are required, that is novelty, security, robustness, and efficiency. So the literature review talks about two kinds of numerical approaches as far as optimization algorithms is concerned. The first category is the deterministic approach, and the second category is the probabilistic approach. The difference between the two approaches is that in the deterministic approach, the methods, they are point to point, that is starting from an initial guess. The initial guess is updated over iterations by iterations, until and unless the stopping criteria is satisfied. Whereas on the other hand, the probabilistic approach are those algorithms which begin with a sample of solutions which are randomly generated, and that sample of solutions is updated iteration over iteration until the convergence is achieved. In order to understand this phenomena, we need to look at a number of examples to illustrate this. So the question is, what is the meaning of these nature-inspired optimization algorithms or the probabilistic algorithms? It means that the nature-inspired algorithms are those algorithms which derive their inspiration from some natural phenomena existing in the world, in the sense that it could be dependent on the way in which the living species they behave, or it could depend upon some other physical phenomena. This is just a partial list of some of the nature-inspired optimization techniques. I said this is partial because, in fact, one of my recent publication is in press, which speaks about a large number of nature-inspired techniques. Every day, lots and lots of work is being done in this area. These techniques are also called heuristics, for the reason that heuristics means that those algorithms which are having the property of self-learning, that is, they learn from their own past experience. Some of these techniques are overlapping, and this is a pictorial diagram to illustrate their relationship amongst each other. So coming to the difference between the nature-inspired techniques and the traditional techniques, as I mentioned, is that the nature-inspired techniques, they search from a population of solution instead of a solution. Now, this is the most important difference between the nature-inspired techniques and the traditional techniques. And therefore, I would like to spend some time on this aspect. Now, let us suppose that we have the famous Newton-Raphson method to reach the minima. Now, this is a hypothetical example, okay? And it's a one variable problem. And suppose the minima is at this point, okay, xk plus 1. We will start with the initial guess according to the Newton-Raphson method and keep on updating this x0 over to x1, over to x2, etc., till the convergence is satisfied, and the best point that we get is termed to be the best approximation which the Newton-Raphson method is able to provide. This is the way most of the deterministic algorithms they work. Now, on the other hand, the probabilistic approach, or rather the nature-inspired techniques, they work on a different phenomena. That is, instead of one solution, we will start with three solutions, let's say x0, x1, and x2. So we are starting with three solutions. It's not necessary, it could be 3, it could be 10, it could be 100, depending upon the computational facility that is available to the user. But this is the way the initial population of randomly generated solutions is prepared, and the next generation is obtained by applying the various operators of the nature-inspired technique, so that the next population is looking like this. So x0, x1, and x2 have changed their position in one iteration itself. And the nature-inspired techniques tells us that as and how more and more populations are generated, more and more generations are executed, most of the points, they are expected to converge to the global solution. Another example to illustrate, here is a two variable problem, that is x versus y. We have randomly generated solutions in the search space. This red dot indicates the global solution, and we are going to perform the generations. So here is the first generation, second generation, third generation, fourth generation, and you can see that as and how the generations are proceeding, the points are trying to converge to the global solution. And in fact, in the 8th generation, we find that most of the solutions have converged to the red dot. Now, the other technique, other differences between the nature-inspired techniques and the traditional techniques is that the nature-inspired techniques, they use some probabilistic transition rules instead of deterministic rules, which means that, for example, let's say in PSO or particle swarm optimization, we will see that the rules, the transition rules have some kind of random numbers incorporated into their formula. So that's why they are called probabilistic transition rules. In the case of deterministic rules, there is no random number, just as in the case of the Newton-Raphson method. It is just a deterministic formula, and that's it. Thirdly, the nature-inspired techniques can be applied to discontinuous and, in fact, to non-differentiable functions also. And they are very simple to program, and any user having a minimal knowledge of computer programming can implement them on the computer. Now, coming to the various classification of the nature-inspired techniques, I usually classify them into the 4 categories: evolutionary algorithms, swarm intelligence-based algorithms, algorithms based on physical law, and the miscellaneous category. The first category is the evolutionary algorithms, which derive their inspiration from living species. Some of the algorithms in this category are the genetic algorithms, differential evolution, evolutionary strategies, genetic programming, etc. As I said, this category of nature-inspired techniques is based on the Darwin's theory of evolution, which has 2 important properties. The first property is the property of inheritance, and the second is the competition. What does inheritance means? It means that the passing of the good features of the kth generation to the k plus 1th generation. Just as in human beings, we want that the good traits of our current generation, like beauty, intelligence, etc., this should be carried over to the next generation. Exactly in the same way, when we are designing a nature-inspired technique, we want that the good traits means those solutions which are having better objective function value should be given preference to go to the next generation. And similarly, in the case of competition, which means that the survival of the fittest, just as you know, during the recent pandemic, we were saying that those individuals who are having high immunity, they are likely to survive this pandemic, and probably the rest of them will die. And that is exactly what is the meaning of this second property of the Darwin's theory of evolution. So this is incorporated into the design of nature-inspired techniques in the fact that each of the individuals is evaluated based on a fitness criteria, how fit it is, that is, how close it is to the minima. Only those solutions which are having high fitness will be given preference to survive, and the rest of them will die. Some of the success stories in this area are the design of high-speed trains. As you know that this is a highly complicated problem when you want to design a high-speed train. And according to one of the Japanese website, it says that genetic algorithm was very, very successfully used in the design of airplane wings as well as the bullet trains. And this is one of the very interesting and typical example of the application of genetic algorithms. The second category is the swarm intelligence based algorithms, which means that the swarm behavior is being incorporated into the algorithm. Some of the algorithms in this category are listed here. And the third category is the algorithms based on physical law, that is the gravitational search algorithm, the central force algorithm, which means that these algorithms are dependent on some physical phenomena, just like the phenomena of gravity, etc. And finally, the miscellaneous category, that is the harmony search algorithm, biogeography based algorithm, and so on. Of course, it's not possible for me to cover all these, so quickly I will touch upon some of them. Now, coming to the historical development, as the invent of computers, Monte Carlo simulation was introduced, which was proved to be quite successful. Then the random search technique came into existence, which basically had two phases. In the first phase, the randomly generated solutions were evaluated based on the objective function. And in the second phase, these solutions were manipulated by local searches till the stopping criteria is satisfied. The ant colony optimization has been proved to be quite successful, particularly in discrete optimization problems. The concept behind this is that the ants, they are following each other in such a path, in such a way that as and how some obstacle comes into their way, then they automatically choose the best, that is the optimum path. And how do they follow each other? They follow each other with the help of a pheromone, which is a scent, which is a perfume, which is secreted by these ants, so that the follower knows where I have to go. And based on this, the ant colony has been very successful in solving the traveling salesman problem and other discrete optimization problems. Now, the genetic algorithms came into existence in 1975. Holland is called the father of genetic algorithms, and today lots and lots of people are working in this area. As I said, this is one of the most important algorithm which is based on the Darwin's theory of evolution. It means that you know that life began on this earth with the help of a single cell amoeba, and over the millions and millions of years, genetic operators, that is the crossover, the mutation, etc., they were applied, and slowly we reached at the stage of human, which is the most intelligent creature on this earth. And you don't know that after some years we may have some superhuman beings as well. So what does it mean by a genetic algorithm? Let's look at one cycle of a genetic algorithm. Initially, the randomly generated solutions are obtained. They are called chromosomes, and each of the chromosome is evaluated based on some fitness criteria, which is user defined, and a fitness test is carried out. That is, those chromosomes which are having good fitness will be retained, and the rest of them will not be retained. The selection is done based on this kind of a criteria, and the best parents are selected. From this set of parents, which is a subset of the population, an operator which is called as the crossover operator is used, and that is responsible to give a sense of breeding, just as I mentioned in the case of the Darwin's theory of evolution. Once the crossover operator is applied, children are obtained with a hope that some of the children will have better performance in terms of fitness as compared to their parents. Then a mutation operator is applied, which is very sparingly applied, and it is responsible for escaping out of the local minima. Like this, one generation, one cycle is completed, and the genetic algorithm means that all these operators are applied over and over again till the stopping criteria is met. So basically, the natural selection is the sense behind the genetic algorithms. Usually, it is mentioned that the GAs are very adaptive and they learn from their experience, and they are responsible for solving the complex problems very, very efficiently. Just as I mentioned, the bullet trains. As I said, genetic algorithms may have different kinds of encoding. There are today specialized genetic algorithms for real coding, for binary encoding, for hexadecimal encoding, and so on. This tells us how versatile the genetic algorithms are. And apart from this, there are the other operators, the selection, crossover, mutation, and elitism, which are repetitively applied so that the convergence is attained. The second operator is the selection operator. There are two important and popular selection operator. The first one is called the tournament, which means that between two chromosomes, a tournament is played and the winner is placed into the mating pool like this. And as you can see in this internal rectangle, the mating pool has been constructed. From this mating pool, the subsequent operators are to be applied. Similarly, the roulette wheel selection is also a very popular selection operator. Then comes the crossover. There are a number of types of crossover operators. Of course, most of them are dependent on the way in which the encoding has been performed. If it is a binary encoding, then accordingly the crossover has to be defined. If it is a real encoding, then accordingly the crossover has to be defined. And on the same lines, we have the various kinds of mutation operator depending upon the encoding. These are just some of the examples, but the list is very long. In general, the pseudocode of a generalized genetic algorithm can be written like this, and depending upon the choice of the user, all these parameters, that is encoding, crossover, mutation, elitism, all these things can be user defined. Then came into existence the most important real coded genetic algorithms. And in fact, this is the area of my research when we began in 2005, etc. We proposed a real coded crossover operator and a real coded mutation operator. And these papers have received lots of citation today. Also, I would like to introduce the concept of mimetic algorithms, which was proposed by Moscato in 1992, and later it was also formalized by Radcliffe. These are genetic algorithms which are trying to incorporate some local search into the genetic algorithm so that the performance of a genetic algorithm can be improved. So this is the idea that local search is being applied at various situations so that the genetic algorithm can be improved. All right. Then we also came up with a concept of self-organizing migrating genetic algorithms. One of my students worked on this concept, and this is the concept where we are trying to look at the various patterns that are available in nature, particularly in plants and flowers. With the help of these self-organizing patterns, we designed the self-organizing migrating algorithm. Now, the swarm intelligence is the second category of nature-inspired techniques. It is based on the swarm behavior. Swarm behavior means that a group of agents, they are flying together in the search space in such a manner that they are communicating amongst each other. In order to understand this concept, I have a small video clip to share with you. You will observe that there are a number of birds which are sitting on this tree. And as and how I click on this video, all these birds will initially, they will fly in different directions, but very soon some communication will take place amongst them so that they will start moving towards the right direction. So please observe the behavior of these birds. These birds are initially going to fly in different directions, but very soon they will move towards the right direction. So here is the video. So you saw that all the birds, initially they were flying in this direction, but very soon some communication took place amongst them and all of them started moving towards the right direction. This is what is called as the swarm behavior. Another example to illustrate this concept. So the idea is, what is swarm behavior? Swarm behavior is the communication that is being taking place between these agents. These are called the search agents. And that is what we are going to do when we are designing a swarm intelligence based algorithm, that these search agents will be randomly generated in the search space and some communication will be taking place between them so that they can all move towards the minima. Coming to the success stories, you must have heard about the drones, which have an important role to play not only in defense, but also in various civilian problems, for example, supplying flood relief and agriculture and so on. So this concept of swarm drones is based on the particle swarm optimization or the swarm intelligence based algorithms. And this is a very important concept as far as the nature-inspired techniques is concerned. So here is again a small video to illustrate the behavior of swarm drones, where we will see that no human intervention is being done. Only the drones are working based on the communication amongst each of them. So that's the idea, that swarm is the concept, swarm intelligence is the concept where each of the search agents is trying to communicate between each other so that the minima is attained. Now let us come at the computational aspects of these nature-inspired techniques. Hello, what happened? Somebody has shared the video. Hello? Hello? I think somebody has shared the video, so my video is gone. Hello? Hello? Dr.
No,
Satyadev?
continue.
I think somebody has shared the video, so my video has gone.
Okay, okay. Let me see.
Let me share again. Can you see it now?
Yes, ma'am.
Okay.
Madam,
Yeah,
it is
I think
visible.
some participant probably shared the video, so my video was gone. All right. So coming to the computational aspects. Sorry, what is that? So how much time do I have more, please? Can you tell me, please? It is 12:06 now.
Almost 20 minutes.
Okay, thank you so much. All right,
20,
so I'll try to.
25 minutes.
Okay,
You
I'll
can
try
take
to.
25 minutes.
Yeah, I'll try to. I'll try to finish up with this step.
Thank you.
Right. So basically, let's move on to the computational aspects. Here you will see that we have a simple optimization problem, which is consisting of n variables, and it's an unconstrained problem. That is, we have the xi, which is defined between the lower and the upper bounds, and as an example, let's take a two variable problem, x1 squared plus x2 squares. Of course, we know that the solution is at the origin, but we want to understand the working of these algorithms. So that's why we are taking a small example so that we can understand the working. The first variable is lying between -100 and 100, and second variable is lying between -1 and 50. Particularly, I've chosen these bounds so that it is not a symmetric, search space. So the general template of a nature-inspired technique will work like this. That is, we will initialize the population pop size, that is the size of the number of search agents that we're going to generate. And we are also going to initialize the maximum number of iterations that the user wants to allow, and generate a population of randomly generated feasible solutions in the search space, evaluate the objective function at each of them, and initialize the iteration, and then carry out a big for loop, that is from iteration is equal to 1 to iteration is equal to maximum iteration allowed, perform the various nature inspired techniques operators, and keep on repeating till the maximum number of iterations allowed is attained. After that, report the current best solution as the optimum solution. So this is the general template for any nature inspired optimization technique. For different optimization techniques, this particular line, that is the operators, is going to be different. Rest of it is going to be same. So the first step is how to generate an initial population, which is to be randomly generated. For this, we are going to make use of the randomly generated, uniformly distributed random number generator on computers, where we are going to generate a random number R between 0 and 1. This can be done with the help of any programming language that you want to use. And we can also scale this small r to capital R, where capital R is expected to lie between x min and x max. This is the way you can use a small linear transformation to give you this capital R. And this can be done for all the coordinates. Of course, you can use some libraries also have a provision of generating a random number between x min and x max. But in general, I thought, let me just try to illustrate that. Suppose you have a random number between 0 and 1. How can you scale it between x min and x max? Now, in our example that we took, the two variable problem we took, suppose for the first coordinate, we had generated a small random number r as 0.16345. This is a number between 0 and 1. And when we want to generate, generate the capital R between -100 and 100, that's how the scaling is going to work. And we are going to get capital R as -67.31. And similarly, in the second coordinate, because our problem is a two variable problem, so that's how the small r is going to work and the capital R is going to be obtained like this. Using this concept, the first randomly generated feasible solution turns out to be this. Like this, we are going to create a population of size, pop size. So pop size is the, again, a parameter which is to be specified by the user. Second step is to evaluate the objective function. So we're going to evaluate x1 squared plus x2 squared. That's it. Just plug in the values into the objective function, because this is our objective function that we are trying to work, and repeat this procedure on all the feasible solutions. So here you see the all the solutions, the randomly generated feasible solutions, have been neatly obtained, and with the help of the objective function, we can record the best and the worst feasible solution in the entire population. This step was till here was common to all. Okay. Now the next step is which operators we want to apply as far as the nature inspired technique is concerned. So there are many ways we could work with. We could work with GA, use the selection crossover mutation, PSO, ABC, etc. So what I'm going to do is okay. Next, the next step is how do you know when to stop? So there are many ways in which you can stop. Although, as I mentioned, the predefined number of iterations is the most commonly used technique. But there are other ways also which I've enlisted over here. So for our working example, let us pick up three very popular nature inspired techniques. And they are particularly chosen because they all belong to the swarm intelligence based category. See, it is important to compare the same category algorithms, otherwise the comparison is not fair. Okay, so that's why I have particularly chosen three algorithms which belong to the swarm intelligence category. So these three algorithms are swarm intelligence algorithms. I can quickly go into the algorithm that is the basic flow of the PSO. That is the basic flow of the PSO. The population in PSO is called as the swarm, and the fitness of each of the particles are the chromosomes. Particles is evaluated. So this, in the swarm intelligence, this terminology is different. Particles and swarms is different. That's why it's called particle swarm optimization. G best is the global best, P best is the personal best, and velocity is the velocity of each particle. We need to modify these parameters and then move each particle to a new position. This is the way the general flow of a PSO algorithm works till the convergence is attained. There are two governing equations. One is called the velocity update equation, and this is the way it works. That is, the velocity of each particle is going to be obtained using this linear combination of the current velocity, C1R1 times P best minus current plus C2R2 times G best minus current. So basically, it is a linear combination of the current velocity as well as the global best and the personal best with respect to the current solution. The second governing equation is the position update equation. Using this velocity, each particle is going to update its current position. Now, coming back to our example, let us take a population size of 6 particles. This is a hypothetical example. So particularly, I have chosen integral values, although in general, these should be real values, but I have chosen integral values just for the sake of ease of our calculation, because I have done hand calculations. So first of all, the first particle is 2, 4, because our variable is x1 squared plus x2 squared, two variables. So x1 squared plus x2 squared gives me 20. Like this, I have evaluated for all the 6 points, and I find that G best is this one, the third particle, -1, 1, having a fitness 2. So this is the global best, G best. Now I will apply the velocity update equation and the position update equation. These are the component wise, they have to be applied. Component wise velocity update equation and the position update equation. And what we find that for the first particle, this is what the calculations give me. And like this for the second particle, third particle, etc. And what do I find? That all the 6 particles have now got this updated position, that is 1.5, 2.7, etc. And I find that the G best is the third particle having a fitness of 1.37. Note that in the first iteration it was 2, now it is 1.37, which means that in the first iteration itself we have got an improvement from 2 to 1.37. Like this, if more and more generations are applied, the convergence is going to be attained. This is the second iteration. Again, you find now the global best has shifted from the third particle to the fourth particle, but the objective function value is 0.13. So imagine how fast the convergence is taking place. Note that these are only 6 particles and we are doing hand calculations. Imagine what will happen when we use the computer and we increase the pop size, the number of particles. The second algorithm I'm going to talk about is called the gray wolf optimization. This is based on the social hierarchy of gray wolves who live in a pack of wolves. The best wolf is called the alpha wolf. Second best is called the beta wolf. And the third best is called the delta wolf. The remaining are called as the omega wolves. So the mathematical model of the encircling behavior of these gray wolves is written in this equations. Usually the gray wolves, they do the hunting mechanism. That is, they first encircle the prey and then attack it. So this is the encircling behavior. Then comes the hunting behavior, how it is going to hunt it. And finally, the attacking the prey. So these three phases is going to give you the attack. That's the pseudocode of a gray wolf optimization algorithm. Coming to our example, we find that the same example, we're going to do the same calculations. And as you can see that the third wolf is giving us the best. And as and how we apply the concept of the gray wolf, we will note how the updation is being done. So in the first iteration, the calculations are shown here. In the first iteration, the updated first wolf is given by 1.11, 2.61. And like this, the remaining wolves are also updated in such a way that after the first iteration, this is what the updated alpha wolf looks like. It is the fifth wolf, 0.012. This is the updated wolf in the first iteration. And like this, in the second iteration, unfortunately, no improvement was done, but never mind, that's the way it works. So a greedy selection is employed. That is, if no improvement is done, then retain the old one. So therefore, 0.012 is the best wolf, that is the alpha wolf. Then comes the artificial bee algorithm. This is algorithm which is based on the design that was proposed by Karaboga in 2005. It mimics the honeybees in nature, which has two properties, the properties of self-organization and division of labor. This is the behavior, the food source, the employed foragers and the unemployed foragers. These are the three components of any honeybee swarm. Swarm is the group of honeybees. They have to pick up the honey from the food source, that is the flowers. And some of them are the employers and some of them are unemployed. These are the definitions, what I am trying to actually say about each of these foragers. They perform an activity which is called as a dance, and this dance is responsible for telling each and every honeybee in the swarm to indicate where the honeybee is expected to find most of the good flowers. So artificial bee colony algorithm has been designed based on this information sharing property of the bees. And we can see that the artificial bee colony algorithm has the following 3 steps. And this is the social behavior of the honeybees. So quickly I can skip this part. Now coming to the calculations, we find that the third honeybee is having the best fitness. This is objective function and this is its fitness. Fitness is 1 upon f. And then we can see that the calculations of the cycle for each of the cycle is shown here. I can't just explain each of this because of lack of time, so I'll quickly skip it up. And what we can see is that after the first employed bee phase, this is what the calculations tell us. The third bee is having fitness 1.001. Then we need to employ the onlooker phase, which tells us that the After the first cycle, this is what the third B looks like. So this is the 0.0362. Okay. Like this, we perform the second cycle, etc. So now, therefore, with the help of these three examples, let us now try to analyze what we have done. In this talk, I have tried to illustrate the iteration-wise performance of the three algorithms, ABC, Grey Wolf, and PSO. I have tried to illustrate the iteration versus fitness of the best solution. So the best solution amongst the 6 solutions that we generated is illustrated over here. Similarly, what is the behavior of the iteration versus fitness of the worst solution of the 3 algorithms? That is illustrated over here. Then let us now look at the way in which all the 6 particles behave. So here in this table, I'm trying to illustrate ABC, Grey Wolf, and PSO. The initial population was same in all the 3 cases. In the first iteration, this is the position of all the 6 particles. Similarly, in the second position, all the particles have moved to a different position. As you can see, Grey Wolf, most of the particles have converged very close to the minimum. So this tells us some interesting features of the 3 nature-inspired techniques we have chosen. Now, the natural question is, which algorithm is the best? And the answer to this lies in the no free lunch theorem, which was proposed by Woolpred and McCarty in the year 1997, which tells us that there is no meta heuristic best suited for solving all optimization problems of varied complexities. It means that all the optimization problems in the earth have different kinds of complexities. Some of them have NP-hard nature, some of them have multiple local minimas, etc. Therefore, you cannot design one single algorithm which will solve the various optimization problems having different kinds of complexities. In order to understand this concept, imagine that when you go to a doctor, depending upon your physical ailment, if you have a heart problem, the doctor will give you accordingly medicine. And if you have, let's say, diabetes, the doctor will give you a different kind of medicines. So depending upon the problem at hand, you have to decide which particular algorithm or which particular algorithm is best suited for you. Coming towards the close of my talk, the first open problem is how to analyze the nature-inspired techniques mathematically in terms of their convergence, stability, and robustness. Now, as I mentioned, the nature-inspired techniques are having lots and lots of complexities and lots and lots of parameters. But mathematically speaking, there is no rigorous mathematical proof of their convergence, their stability, and robustness. So this is an open problem, and anybody who is willing to devote his research career can think about this open problem. Secondly, the fine-tuning of the parameters of a given algorithm so as to achieve best performance for a given set of problems has also to be obtained. Like, for example, for a given set of problems, somebody may propose some parameters, another person may propose some other parameters. But for a given set of problems, a common set of given problems, it needs some kind of a research and an analysis to obtain the fine-tuning of the parameters. The third problem is the design of new type of benchmark optimization problems, which means that mathematically speaking, you could propose new benchmarks so that more and more complexities can be introduced. The fourth problem is to identify the most suitable performance matrices for a fair comparison of algorithms. Like in my talk, I mentioned the fitness of the best solution, fitness of the worst solution, and the search space, how it behaves. These are just 3 examples that I've chosen, but there are hundreds and hundreds of other ways in which matrices can be used and designed to evaluate the performance of the nature-inspired techniques. People use mean, standard deviation, other statistical t-tests, etc. But still, a lot of scope of research is available in this direction. And finally, the concept of scalability, that is how you can scale the algorithms so that they can solve real life problems efficiently. Because you know that in reality, the real life problems are very, very large dimensions. So finally, I would like to highlight some of the research work that we have done at IIT Roorkee with the help of my 20 passed out students. Genetic algorithm was done with the help of these students who are now well placed in different parts of the country and abroad. Particle swarm optimization is also a good area, and recently these students, they have worked in various nature-inspired techniques. And currently, the following students are working with me for their PhD. I would happy to share that I am writing a book, Nature-Inspired Optimization Techniques, an Introduction. It is in press. And there is another very interesting book by my very good friend, Xinxi Yang. This book is also available. I think it's available online as well. And in fact, I'm going to organize a workshop. It's going to be a summer internship workshop on nature-inspired techniques with the help of Professor Xinxi Yang. So thank you so much for this patient hearing, and I would be happy to answer any questions. These are some of the announcements. I'm the president of the Soft Computing Research Society and the executive editor of SOM Intelligence and the general chair of a series of international conference. We're going to have this conference in IIT Mandi, and I'm also the series editor of this Algorithms for Intelligent System. So any questions, I'll be very happy to answer. Thank you so much.
Thank you so much, ma'am, for your provoking lecture. Now participants can ask their queries. Also, I request the host to unmute everyone for some time so that they can ask their queries. Yes, anyone from the audience who wants to ask any question from our speaker, Professor Kusum ma'am.
Maybe you would like to type the question on the chat box. Yeah, I think there are some questions. Okay, so here it is. Let me just go through the beginning first. Okay. Okay. Okay, somebody saying, please share the PPT. Sure, I can do that. That's not an issue. Please take benefit of listening such legends in optimization due to internet connection failure, going disconnected. Okay. Then very interesting lecture. Thank you so much. Thanks a lot. Thanks a lot. Excellent, ma'am. Thank you, Professor, for the education lecture. Very interesting, very informational. Oh, these are all praises. I want some criticism, please. Come on, everybody. Thanks for these nice words. Let me, I am more interested to listening to some criticism. Okay, so here is one. I actually came late for the class. We are all going to get the recording. How do we take the performance of optimization techniques in neural networks? Oh, well, thank you for the question. Yeah, so here is this question. How do we take the performance of the optimization techniques in neural networks? Okay, so let me just throw some light on this. See, the performance of a neural network will depend upon the way in which the weights are selected. So the training of the weights is done with the help of a deterministic algorithm, usually the gradient descent or the steepest descent. This is a deterministic algorithm. And as I mentioned, vis-a-vis the deterministic algorithm, we have the nature-inspired techniques. And if you use the nature-inspired techniques, you are likely to get better results. So that's the way this neural network performance can be enhanced. So I hope I've answered your question. Okay, another one. How do we rate the performance of the? Actually, that is the same one only. Please show slides on global minima and maxima identifiers. Okay, sure. Let me just share it again. Share. You want me to show? down the lane. So somebody wants to see this on global minima and maxima. Where is it? It's in the beginning. Yeah, here it is. This one. So here you can see this is a two variable problem, x1 over here, x2 over here, and the z direction is the objective function. So here there is a peak. So this is a global maxima. There is a local maxima. This one's. These are local maximas. These are the local minima and the global minima. So local one is little up and the global minima is little down. So you wanted to see this. Okay. Right. So what else? Then thank you. Ma'am, which book you recommend to beginners, students? Okay, that's what I just now shared in my, it's there. There are two books, one which I have, my book, it is in press. It is going to be available very shortly. And the other is the Xinshi Yang book. That is a very good book for beginners. And I mentioned that I'm going to organize a short-term course, a summer school course in June. So if anybody is interested, you can please contact me. You can just write a mail to me and I will share with you the details for attending that. All right, then can we have the presentation slides? Sure, we can. I will just send it off to the organizers. Then there is, which software is best for optimization? Okay. Now, unfortunately, this is a very vague question because what do you mean by which optimization algorithm? Okay. So depending upon the optimization algorithm which you're looking for, accordingly, the software has to be designed. Okay. Usually, I don't recommend any built-in softwares because the reason is, like for example, if you use, let's say MATLAB, okay, then what particular algorithm is being used by genetic algorithms, what particular parameters are being used in genetic algorithms is not being mentioned, and you are not in a position to modify the parameters of the genetic algorithm as far as the genetic algorithm in a black box is concerned. So I usually do not recommend softwares for optimization. I usually encourage my students to write their own code for any particular algorithm that they want to design. So usually I don't like to use the softwares which are black box. Okay, thank you for your lecture. Could you please supervise PhD students who are interested in this? Oh dear, actually, it's difficult to supervise. It is difficult to, take in more PhD students. At the current moment, I have 6 plus 2, 8. 8 students working with me. 20 of them have already passed out and they are now working in different positions in India and abroad. At the moment, 8 students are working with me for PhDs. I don't think I can take more at the moment, but sure, I can help you out with any particular problem if you have. Thank you. Shortly, next speaker is going to, okay. Where is the best section to implement meta-heuristic algorithm in neural network at the learning stage or at the retrieve stage in the case of neural network? Okay, actually, see, as I said, till today, neural networks have been trained with the help of the gradient descent and the steepest descent. Okay, but very little research has been done in applying the nature-inspired techniques in the training of neural network weights. So it is a open problem, and lots of work is still required in this area. So of course, the sky is the limit. Okay, can you put your email? Oh yeah, I'll put my email, not an issue. Please stay connected for next lectures. How can we connect you? Oh, you look at my website, please. You can just put in Kusumdeep in Google and you will get all my information. But I am happy to put my email in the chat box. Thank you so much. Thank you so much, everybody.
Ma'am, thanks for delivering your lecture. Madam, Punjabi University Patiala feels proud to have you as a resource person today. Thanks for your valuable lecture. Now I request to host of this webinar to award the Certificate of Appreciation to Professor Kusum ma'am.
Thank you.
Thank you. Thank you, ma'am, for being
Thank you
with
so
us
much.
and spare time from your busy schedule.
Thank you. Thank you
Now
so much.
thank you. Thank you, ma'am. Now I hand over the stage to Ms. Savita for the second session of this webinar. Thank you. Thank you, everyone.